I'm Ahmed Daud, and in this session, we are going to start discussions on hyperparameters of decision tree classifier or decision tree regressor provided by sklearn. Okay, so one of the important aspect is that I told you that how we can control the growth of the decision tree or how we can put the restrictions on the algorithm which is growing that tree. Okay, so by I told you that we can pass some values to these hyperparameters to control the growth of the tree. But keep in mind, all the hyperparameters are not for that purpose. They are like first hyperparameter criterion. It actually not to put the restriction on the growth of tree, but it change the way of splitting or change the impurity measure. Okay, on which on the basis of which impurity measure it will split. Okay, so it will not disturb or not put the restriction on the growth of tree. It just change the impurity measure. In the second, hypermeter is also not for the restriction of the growth of the tree, but the max depth, mean sample split, mean sample leaf, mean weight fraction. These are the hyperparameters that can restrict the growth of the tree. Max features also have not this type of purpose. Random state is to control the randomness. Max leaf node, mean impurity decrease. These can be, uh, you can say, control the growth of the tree. Class weight, again, it is for another purpose. Also, this can control the growth of the tree, but it actually not control the growth of the tree by the way that other hyperparameters doing. It actually gives some weight to the some samples, and that's why the whole structure of the decision tree change. And there is this hyperparameter CC P alpha, which is actually called the complexity parameter. For this session, just you can say ignore this hyperparameter because it actually belong to the part of post pruning. So in the post pruning, we will have a deep discussion on this hyperparameter. Okay, so without wasting time, we will go towards the not book up. And here you can see I have just taken an image from the documentation that I was showing you, and we will start one by one. Okay, so first of all, criterion. You are already familiar about the Gini impurity, entropy, and log loss. If this criterion, you will pass some value, and according to that impurity measure, the our algorithm will use the splitting part. Okay, or do splitting on the basis of the impurity measure that you will mention, and by default it is Gini. Second one is splitter, which is quite important. Hyperparameter, and the purpose of splitter is not to control the growth, but the purpose is to make some randomness or to speed up the process. Okay, I will tell you what is splitter. Okay, let's say you are at this particular node and you now have to split this node into some childs to decrease the impurity. Okay, so for that purpose, what you usually do, you see the split values of each feature and select the best split value to make here a decision rule. Okay, in this box, you make a decision rule like uh, uh, the value should of a feature, let's say f2 should be less than 3. Okay, will go towards this side, and other features, other data points will go towards this side. Okay, you select some split value of some feature. Okay, so what splitter do, splitter has two options. One is best and second is random. Okay, what is best? Best is exactly the same that we have discussed before that. Let's say you have four features, f1, f2, f3, f4, and there is one target variable. So at each stage, what do you do? You see the each value of each feature, and you do calculate some Gini impurity. If you do a partition at this point, what will be the Gini impurity? If you do partition at this point, what will be the Gini impurity? You do see all the split values of f1 and select the best split value for this feature f1. In this way, you select the best split value for f2, then F3, then F4. Okay. For the feature one, you have some values in its column, and you will you will select some uh, you can say you have a lot of values from and in F1 there is some minimum value, and there is some max value, and in between mean and max value you calculate the Gini impurity for each threshold, and which uh, threshold or which split value give you the minimum Gini impurity, you will select as a best split value for that feature F1. In this way you do for the F2, F3, F4. Okay. And now all the features have some best split values. Then again you will compare between the best split values of all the features, and which feature is giving you the best split value, or means it giving you the lowest Gini impurity, you will select that. Means best out of four best split value you select. This is the case when you have passed the value to that splitter best. This parameter, if you select the best value or this string to that hyperparameter splitter. But if you will pass the random, there will be a little bit different case. In the case of random, when you will pass the random value to this splitter, it means when you have the four features, it will select a random threshold between the mean and max value of F1. Okay. And calculate the Gini impurity for that. And then it will select a random split value between mean and max of F2, and calculate the Gini impurity. Then it will select between mean and max of F3, randomly select a value, a threshold, and calculate the Gini impurity. And then for the F4 case. Now you have four randomly selected split values for against each feature. Okay. Now you select and now you will compare the Gini impurity of these four random selected split values, and which random split value is giving you the lowest Gini impurity. You select that random split value to split or to make a rule at this stage. Okay. So you are selecting best of four random values, best out of the random thresholds. So that's why they also say that best random split. If you will see the description here, it is saying that this strategy used to choose the split at each node. Spot strategies are best. Best is to choose the best split. Okay. And random value to choose the best random split. You select a random split value for each feature. Okay. Then you select best out of these selected random split values. So this is for the case of splitter hyperparameter. So you can get an idea. It is not actually controlling the growth of tree. It is you can say creating some randomness in the decision tree, and also it is speeding up the process because of searching the in a feature the whole bunch of values can slow down the process. Okay. But the main purpose of splitter, you will get an idea in the random forest model or random forest module. But for now you can get an idea of what is meant by best value to pass splitter, and what is meant by the random value passed to the splitter. Now we will go towards another parameter, which is maximum depth. And you already know that I have told you in the previous sessions that it actually control the depth of the tree. Whenever you will pass some value to maximum depth, it will control. Like here, if you have passed the value depth is equal to tree, it will not grow further the depth of tree. It will restrict the growth of the tree at this position. Like if I will have here some example, you can see like this one is maximum depth is 2 here, and it has grown this tree, and this algorithm does not go towards or did not go towards the further splitting after achieving the depth 2. Okay. So further there is a hyperparameter which is minimum sample split. Okay, so what actually this mean? It is saying that this minimum number of samples should be at each node if you want to do splitting. Okay, so let's say if you will pass min sample split the value to this hyperparameter is equal to 4, it means that if you are splitting from this node to further, it will check how many samples are present at this stage. If there are four samples uh, or greater than four, then it will allow the splitting. If there are three samples at this node, it will not allow any splitting further. Okay, and you can see here, let's say in this case, a okay, so in this case, this particular node on which I have drawn a black circle, this have 33 samples. Okay, and it is doing further splitting. But if in the hyperparameter you will mention that minimum samples should be 34 if you want to do splitting on that particular node. So it if you pass this value to the hyperparameter, then this splitting will not allowed here, because it will say that there should be minimum 34 or greater than 34 samples should be present at this node if you want to do further splitting. So this is the main purpose of min sample split. So minimum samples should be required to do splitting. Okay, so you can pass int value to that hyperparameter, and you can also pass the float value. What is meant by float value? You can pass some decimal value, like you can pass 0.2. What it will what is meant by that, it will consider, if you pass this type of value, it will consider that value as a fraction, and it will multiply the whole number of, let's say if you have total 100 data points on which you are building a decision tree, then it will multiply the fraction that you have passed, and 0.2 will be 20. Okay, so it will consider that you have passed 20 value to this min sample split, and it will consider that there should be minimum 20 samples at each node if you want to do splitting. Or in other words, you can, for simplicity, you can say if you will pass some decimal value to this hyperparameter, it will consider as a fraction this value. Now further, there is another, you can say hyperparameter, which can also control the growth of the tree, which is the minimum samples at each leaf. Okay, what actually it will do, if you do some splitting at a node, let's say this is a node and you are splitting this node into two leaves. Okay, you always in the like we are using cart algorithm, it will produce binary tree, so you always produce two leaves. So this value restrict the, if let's say if you will pass min sample leaf is equal to 4, then if your splitting of this node is uh, you can say generating the leaf which are having samples 4 or greater than 4 at each leaf node, then it will allow that particular split. Okay, it means the minimum number of samples required to be at a leaf node. Okay, a split point at any depth will only be considered it if it leaves at least the mentioned value in this training samples in each of the left and the right branches. Okay, if you are doing splitting, there should be minimum number of samples at in each leaf node. If there your split your splitting of the node will not, let's say if your splitting of node is this one, and on this side there are 10 samples, and on this side there are just two samples, and if you have mentioned mean sample split is equal to 4, then this will not be allowed, because it is not generating the leaf that is having 4 or greater than 4 samples in it. Okay, and here if I will show you here, in this case, let's say if you will pass here minimum samples leaf is equal to 2, then at this particular stage, like this node is splitting into two parts, one this and one is this one. So this leaf node has 32 samples and this leaf node has one sample. But if you have passed a min sample leaf value 2, then this split will not be allowed, because this and this right child or right leaf is having just one sample. Okay, in this way you can also put some restriction on the growth of the tree by restricting the number of leaves at each leaf node. Okay, you are putting some restriction that there should be minimum number of samples at each leaf node. If you are going towards the splitting, you are telling to your algorithm. Okay, so there is another mean weight fraction leaf hyperparameter. It has same type of purpose, but here the working is different. It is saying that minimum weighted fraction of sum of total of weights of the samples should be at each leaf node. Okay, I will explain you in with an example here. Let's say, okay, so okay. So till now we have not done any code in which or any we have not used any data set in which we have passed some weight against each sample. Okay, but actually there is also in a lot of cases we have discussed that sample weight is means that this sample has this percentage of weight. Okay, I will you explain here an example. Let's say you have one this data set. Here you can see this data set in which you have two independent variables A and B, and there is one dependent variable which is target column. Okay, and there are just four samples in this data set, and which have index 1, 2, 3, 4. Okay, there are just four values in the A, 0, 1, 2, 3, and you have I have not mentioned here the values of B and target because it is just for the explaining purpose. So here you have mentioned that sample 1 have this weight, sample 2 have this weight, sample 3 have this weight, sample 4 have this weight. It means usually we consider each sample as a sample, okay, as one sample. But here it is saying that this first sample should be considered as a one sample. Second sample should not be considered as a one sample, it should be considered as a zero point 0.7 sample. This means that this particular sample has a weight of zero point 0.7. So you can say here that this particular sample at the index 2 uh, is less important compared to the sample at the one index. If this will be 0.5, you can say this is half of the this has half importance compared to the sample at the place 1. Okay, so and in the like here the sample number 4, you can consider it has a double of the importance compared to the sample at the 1th position. Okay, so it means that you are giving some sample weight to each sample. Okay, what usually do in that case, if you have minimum weight fraction leaf, it will say that if you will pass some value to this mean weight fraction leaf, let's say you will pass here the value 0.3. Okay, mean weight fraction leaf. So what will happen, first you will consider how much total weight of your data set you will add. Usually we count our total number of samples, like there are four total number of samples, but when you are considering the weight of the samples, you will consider the total weight. So total weight of the data set is 3.9. This is 2, this is zero point 0.2, this is zero point 0.7, this is 1. When you will sum all of them, this will be 3.9. So this data set have 3.9 weight. Okay, or when you added weight or total weight of all the samples is 3.9, you can say. So what is meaning by this mean weight fraction leaf is equal to 0.3? It means that there should be 30% of the 3.9 sample should be at each leaf if you want to do splitting. Okay, you can see here what you will do. You will multiply 0.3 with your total weight 3.9, and it is generating a fraction, weighted fraction 1.17. So there should be weighted fraction 1.17 at each leaf node if you want to do splitting. Let's say if you want to you have considered the splitting at the point uh, A feature less than or equal to 0 0.5. If you have considered this as your best split value, then what will happen? You will separate your data points, your all the data points that are at index 2, 3 and 4 will be on the right side, and all your sample at the index 1 will be on the right, on the left side. Okay, now you will sum the weight of the samples. Here your sum of the weight of sample is 2.9, but on the left side your total weight sum of the samples is just 1, which is less than the 1.17 that you have considered here should be at each leaf node. So you can say that this split will not be allowed, because you are saying that your mean weight fraction leaf or your minimum weighted fraction of 30% of your total weight should be at each leaf node. Okay, if you have selected your decision rule as a less than or equal to 1.5, then there will be two samples on the left side and two samples on the right side. So when you will sum here, there is a sum is 1.7, sum of the weights of samples here on the left side, and 2.2 on the right side there is weighted sum. Okay, so this is 1.7 again. It is greater. 1.7 is greater than. Sorry, 1.7 is greater than 1.17 that you have mentioned, and here 2.2 is also greater than 1.7, then this split will be allowed. If you have used your sample weight and you have passed here some value, then in this way it will calculate. And if you have not mentioned this, you can say this value, you have not specified your sample weights and you have passed here some value to this hyperparameter, then it will consider that each sample that you have in your data set will be of equal importance. Let's say each sample should be considered as a one sample. Okay, so remaining hyperparameters and discussion on the hyperparameters we will continue in the next session. So for now,